Thank you again, Gia, for the introduction. So I will basically talk about this predictive side of things in terms of dealing with data from Industry 4.0 or IIoT, or trying to see the rules of systems and dynamic systems and the data science, how we would interplay in one aspect. I think today is a good time to recall what happened 5 years ago, right? And this was the big event that pretty much shocked the world, that the DeepMind, the AlphaGo program, defeated the world champion in Go. And so that's really just exactly 5 years ago on today. That's the date in Asia, okay? I think in the US it's also the same, March 19th now. So let's just say what's coming in this data domain. I think we are in the era of big data. You hear this 4 V's, volume, variety, and also velocity and veracity. Okay, so I don't have to explain them now for most of you. Basically, the data or big data technology or what's going on right now made us think beyond the box. Okay, for a lot of the directions, it's really increased by orders of magnitude. So I think that's the setting we're trying to see how dynamic systems and control systems can be part of this thing. We know that we are surrounded by these applications of data science and big data. For example, things from Amazon recommendation systems, from Netflix and from Google. We're using them every day, and we're also generating tons of data every day. So that's no doubt it's with us. Now, for what's interesting to the topic today is actually what's going to, this thing is going to change the industry. So there's a big drive towards Industry 4.0, and that's also a popular term. So I don't have to explain what it is. And you can see this around this circle, there are technologies that's big data, IIoT, and also cloud computing and other things. Okay, so to summarize what we're expecting from Industry 4.0 is actually we're trying to do 2 things. One is to propel breakthrough improvements in safety, reliability, and productivity. The other thing is to drive intelligent decision making using data analytics and AI. So you can see the data and AI are there, and also it looks like we're going to get the safety, reliability, and other things that was not easy to optimize or automate. That's going to be driven towards more automated solutions. Okay, so for this smart manufacturing or versus data analytics, I would use this chart to just to get us focused on. Basically, for let's say in manufacturing systems or what's in the Industry 3.0 stage, we basically have a sequence of manufacturing steps, okay, or process that's going through processing the products and so on. So above the red line I draw is basically the process side, and there are disturbances in there, and then below the red line there is the control system, okay? And we have a multi-level control to make sure things processed at each step are going to be on target. We generate lots of data by doing control and installing sensors, and these data are also collected for monitoring purpose, and that's been practiced for 20, 30 years at least. There's also other things beyond this part of the process. We make products, okay, we deliver services, and those are all measured by some quality indices. Either it's measured in the lab or measured online or measured by images, okay? And this quality data are the targets of a lot of the manufacturing processes, and we're trying to build the connection between the manufacturing conditions and the product conditions. Therefore, we can infer quality and also monitor the quality. And that will lead us to supervised monitoring as opposed to unsupervised monitoring. And for both things, it really gives us the ability to do smart manufacturing. That is to extract actionable knowledge from real-time data. Okay, so I'll bring one message first, and then another message. Then I'll try to beam down to the particular aspect. I think data science and systems can really work together. Okay, so first thing I would mention is that I see data science is a way to see the dark side. Basically try to get more understanding of the uncertainty. All right, this is on the right side. I have this flying the airplane. I use this as an example. Okay, for the airplane, we know pretty much everything about it. We design it and we test it, so we know all the engineering principles behind it. Okay, and that's called the white side. All right. But when you fly an airplane through this storm or any time, there's part of that you don't know, which is the ambience. Okay, the surrounding, what's surrounding the airplane when you fly through. So the sensors around the airplane or other things we get data from can help us understand what we would not know that's beyond the airplane. So that's what I say that additional sensors or IoT will provide more data on the airplane side as well as on the environmental side. Okay, so the challenge is to basically how to learn the dark side from data, and that will bring us intelligence. So I use this symbol that's pretty much in the Oriental philosophy, that you have the white side and you have the black side. Okay, that's yin and yang. So what you know part of it, but there's the other part that you will not know. Hopefully we can use data to make the dark side better known or become white. So that's one thing I would say data science or data analytics can help us understand the surrounding or the environment better over time. And the other message, since the audience is coming a lot from the control side, I will try to draw the difference or analogy between data analytics in this setting versus system identification. Okay, I'll basically focus on the left-hand side, which is what I call system data analytics, and you can check the system ID side, which is more familiar to the audience. I would say for data analytics, we deal with operational and multi-source data rather than designed experimental data. We have to handle high collinearity because they are not excited fully. They're not designed by any experiments, so they can contain partial dynamics, but not fully excited dynamics. The purposes are also different. Okay, for ID, you're trying to get the true model of the system. You pay the price of exciting the process. Okay, that's what you have to do. But for operational data, data analytics, we're trying to extract features so that we can do better monitoring and fault diagnosis, interpretation, and also prediction of what's going to happen. Okay, so it's really a behavioral kind of analysis for this system data analytics. So keep those things in mind. We're not going to have fully dynamic, but we're going to have some dynamics. And then this is where I see that systems theory and data analytics should be integrated. So let's focus on data that's time dependent. Okay, because a lot of the success in big data, they actually don't pay much attention to time-dependent data. So, but for manufacturing and process systems, we have to look at time dependence, and that's the dynamics. In econometrics, it has been the focus. Okay, there are a lot of studies in the econometric time series analysis, and this is one thing that shows the unemployment rate in the United States. Okay, you cannot say that there are 50 independent unemployment rates going on. They are highly correlated and cross correlated. So that's the nature of what I would call operation data. If you then look into some other systems like this power grid stability, this is in Texas, wind farm locations are measured by PMU, and then you can see this this phase shift. They look similar among all different stations. However, there are times that they'll be different. Okay, they're different here, different there. So that will give us the generally highly dependent or collinear data, but we have to find ways to detect when they are not the same. And for a paper making system or machine, this is one set of data I got years ago. There is sometimes the paper on the machine can break. Okay. So this is right before it's going to break. You can see things starts to oscillate, and then by this time, when it's like that, so the paper is already broken. Okay, so then that one has to shut down the machine. And for chemical manufacturing, this is one of the multi-column manufacturing processes. It looks pretty complex. Okay, so it's almost like a complex network with recycles and feedback. So what you can focus on is that there's this part that you send the raw material feed, and then this is where you collect products. Okay, it goes through the process in pretty much this path to give you the product, but you don't necessarily make the products to good quality, so you have to recycle it back. Okay, therefore, what you pump out is going to be meeting the product spec. So when you do this recycling in this process, the good thing is you will keep the quality under control. The bad thing is that it'll sometimes generates oscillations all over the place. Okay, so and that's the typical kind of oscillation data you can find in a lot of these kind of chemical plants. And the question is, where does this oscillation started from? That's a big task to do this data analytics. And I'll show you the kind of data. This is real data from that plant. It'll look like this. So it's when it's oscillating all over the place, it's hard to know where is the source. Okay, so now let's say in this modern day now, we're going to add more sensors to the manufacturing system with, say, Internet of Things or IoT. This one statement I have here is that when these more sensors are installed, it doesn't mean the dimension of the dynamics will increase proportionally. Okay, so therefore, we'll have more and more measured measurement sensors. However, we'll have to figure out what's the underlying dimension of the dynamics, which does not increase proportionally with the number of sensors. Okay, so that's the task. We have to focus on modeling dynamics in a smaller subspace. So let's hypothesize or make this very, very, very simple problem. Okay, let's say I have three hidden things that's happening, but I measure five. I have 5 sensors measuring, so you can see the number of measurements is greater than what's causing it. Okay, and then I will make just one of them being dynamic, like this one. Okay, and the other 2 are random noise. So here's the problem. Okay, we know the data, but then what's driven the data are really the hidden dynamics we want to figure out, and they're unknown. That's what I call the dark side. Okay, so the question is, how can we extract the hidden or the latent dynamic factor from the measured data of 5 sensors, and then we can capture that dynamics and analyze it. Okay, so that's the task. So now let's go back to the analytics and see what are there for us to use. So I will introduce PCA and hidden alcohol models. Okay, let's look at PCA. If you would apply PCA, then you have data. Okay, this is the measured data in Y. All right, and they are sequenced in time from K to K+1 and so on. So, and what's driving this data is believed to be driven by the principal components. Okay, that's hidden, but you can calculate them. And that the purpose of doing PCA is to find fewer components that will be pretty much represent the variance in the observed data. So there's a very clear dimension reduction in PCA. However, PCA doesn't build dynamic connections. All right, so there's no connection between time K versus K+1. So in this hidden Markov model, there's also the hidden factors T here. However, it's built in the time dependence from K to K+1. Okay, so that's the HMM that has built-in latent time dependence there. Now, what we're looking for is this. We're looking for is both time dimension reduction as well as time dependent latent variables. Okay, so this is the latent sequence we're trying to figure out. And for K+1, it needs to be dependent on the previous times, maybe up to K-P times. Okay, so this is a different model. However, with this model, we have explicit dimension reduction. I'll show that. Basically, the dimension of data is going to be greater than the dimension of the latent things we're trying to figure out. And then we basically enforce upon the strongest time dependence that we're searching for the latent sequence. Okay, so now how do we do this? You might say, okay, if you're looking for the most time-dependent or predictable ones, you might just do 5 separate time series modeling of each of the measured sensor. And then you say, okay, I'm going to pick the most predictable one. Maybe this one is most predictable by eyeballing. The drawback of this approach, of course, is you're throwing away the other 4. Okay, so we're not making full use of data, and that one that you picked may not be representing well of other variables. So the proposed approach is this. Okay, we're not going to throw away any measured data. We're going to linearly combine them or project them with a projection R. Okay, and then that'll give us a latent variable, which is not known until we know what R is. But we're trying to make a model out of this unknown sequence T, okay, and then predict itself so that it can be made most predictable. So this is our new way of extracting latent time-dependent sequences. Okay, so that's the idea. And to make the latent prediction with the T sequence, this is one AR type of prediction, okay? And then if you want to make it most predictive, you can minimize the prediction error here, okay? But the question is, this T here is not known yet until we figure out the projection R. All right, so now let's get the one slide I have, which has equations, okay, just to see what PCA does and what this dynamic latent component analysis would do, okay. So PCA is on top where you find the lower dimension T to minimize its error to represent the data, okay. Now for dynamic latent variable analysis, let's say dynamic PCA, we will do this. We will minimize the difference between the prediction from past data and to the current latent data. Okay, so basically treat T as its own
latent sequence and as if it's data, but it's figured out from the real data Y. So there are two sets of unknowns to be figured out, R and also beta. Okay, these are the unknowns. And then if we do the dynamic canonical correlation, it's just changing the constraints from constraining the norm of R to constraining the norm of the latent scores. So there is some detail that I gave these papers to for you as a reference, that they are described in these papers as how to solve those objectives with the constraints. Okay. All right. Now I'm going to show two examples. One is a toy problem or fairly realistic problem. This is the Lorentz attractor, which has 3 dimensions described by these 3 ODEs. It's representing very complex dynamics. It's in 3 dimensions, but I want to project it down to 2 dimensions that is most predictable. Okay, that's my task. So for this 3-dimension thing, if you look at different angles, you get different pictures on there. Okay, so now I want to find one angle that I'll see most dynamics. Okay. So that's the data here in red. Okay, and the fitted the dynamic 2-dimension thing is in green as fitted through the data. Okay. I'll show that 2-dimension that's most predictable. Okay, that's the dimension in which all points are going to be best predicted by its past. Okay, these are not any one of the x, y,
z's, but it's combination of x, y, z's. And then what's left in the residual direction is very small, as you can see. That's the 3rd dimension. So this one shows the ability of dynamic latent modeling to reduce dimensions and reduce so that what you see is going to be the most predictable dimensions. Okay, now let's go back to the chemical plant data I mentioned and see if we can detect the features we want. Let's feed it through the analytic algorithm, DICCA, and then what we get is this. Okay, we have a dynamic latent features, and you can see the dynamics will have a descending order. First one is most predictable, then it gets less and less predictable. The first one actually corresponds to 3 physical variables very strongly. Okay, and then the strongest one is actually ambient temperature, which is on the left. That's identified now. So ambient temperature affects the operational process, but there's not much we can do. Okay, that's just natural, the nature there. But the second and third components are most interesting. These two have the same oscillation period of about 2 hours. Okay, and that's really what's the cause of the plant-wide oscillations. So I'll show this first 3 dimensions in this what I call tornado charts. You can see the second and third one really goes up straight, and that's related to the cause of the oscillation. So if I animate that, it'll look like this. Okay. So now let's say with this dynamic reduced dimensional modeling, what can we do? We start from the plant that might have some problems. So we'll collect data, operation data only, okay? And then we convert them or feed them to this dynamic analytics, and then pick the features. That's really the part we want to see what's causing it, and then fix the problem. So this is a real thing that's done with that plant. So before this problem was fixed, you can see there's a high oscillation around this level. This is the throughput variable, okay? And then after it's fixed, you can see the throughput has improved by like 15%, and also the level of oscillation is almost gone, okay? And that's the power of this. So I've used pretty much less than 30 minutes, okay? So I'm trying to catch up a little time here. So I will just point out that this framework is related to a lot of work that's done in the past. Okay, this one paper here really highlights what are related to this work in the literature. This is a long paper, it's about 20 pages, just appeared last year. So I'll just provide some slides here for you to see the same sort of mechanism is being studied elsewhere, but with different twists, okay? In statistics, this is the George box, okay? Studied about 40 years ago, but then it's getting to the right sort of solution just in the last couple of years. And this is where it's really causal in dynamics, and it's really relevant to what we are doing. And then in econometrics, that's also a big task to really see what's independent dynamic behind high dimensional data. In subsurface identification, that's more in the systems control domain. IFAC started about, again, 45 years ago, okay? And then it gets really crystallized in the 90s for subsurface identification. And that's relevant to what we're doing. And there are also like linear Gaussian state space representations, and that's using expectation maximization to estimate latent dynamic models. And that's another related path. And then in machine learning, not surprisingly, almost everything people studied is touched upon by machine learning people. And these are the three papers that's actually trying to explore either slow features or predictable features or forecastable components. They are pretty much doing, trying to do the similar things as we do. Okay, so it's really a lot of things in the literature that can be looked at and also borrowed to work on the data from dynamic systems. Okay, so let me conclude. What I covered is really, I'm trying to sort of say that data analytics bring knowledge of the dark side, okay? And then it complements the white side. We're not trying to replace the white side, okay? Analyzing data from dynamic systems will require a new framework because the data is time dependent as well as noise. And also operation data are not fully excited, okay? They're partially excited in dynamics. Therefore, it's requiring latent modeling. And then the latent dynamics have reduced dynamic dimensions, and that'll facilitate interpretation, prediction, and inference. Okay, so I think there are a lot of other things like monitoring can be built upon this framework. Finally, I'd like to acknowledge my co-workers, collaborators, especially Mr. Yiren Liu and Dr. Yining Dong, who is now with the data science school here. And there are external collaborators, my former student, who is now an assistant professor at Waterloo, and then Mr. Liu, who is a PhD student at USC. Okay, that's what I have. Thank you for your attention.